Hello everyone. So really quickly, I made this video to walk us through some of this math specifically and some of the processes of solving specific problems in this last level 3 assignment what we can learn from Starlight. I hope this is helpful, and just to be transparent about what I'm going to do with this video, I'm trying to really get us to focus on the concepts once again. There is a bit more math in this one, right? And hence why I wanted to make this more of a walkthrough of specific problems to help you really appreciate each step. And along the way, you'll definitely get little side notes about stuff like scientific notation, stuff like units, and finding significant figures. Now, these are things that are important, and this is definitely not the last time we're going to see them. But I want you to keep those things in mind, but not pay them as much attention, if it's okay, with the concepts themselves. How to find basically the differences of the mass, for example, in diffusion problems, or really understanding the relationship between wavelength, frequency, and speed of the wave. So once again, I hope this is helpful. Let's just get to it. Okay, so let's look just with question number 1. This is something that if you feel comfortable enough doing so, you can actually apply it to 2 more values in number 2. I'll try to briefly talk about this, but let's just briefly read what we have here. Now, our question reads, what is the frequency in hertz per second, s with a little -1 exponent, or 1 over s? I'm just going to note that because I want to get back to that at some point. 1 over s potentially, of a red light wave of wavelength lambda, right? 700 nanometers. Nanometer is 7.00 times 10 to the -9 meters. The speed of light is 2.998, 10 to the 8 meters per second. Now, let me just quickly underline this number. I'm going to get back to this because you could have gotten one of 2 responses that you can really easily get from this problem. One of them is correct. One of them is a bit of a mislead on my part, and I'll explain what that means. For now, let's just focus on what we have in front of us. So what I like to kind of do whenever I see a problem like this is to tell you that if you are a little bit confused in terms of how to start, don't focus on what you necessarily aren't super sure about, right? That will come in time. Focus on what you know. And this is not just some way of making you feel better. This is an actual strategy for this, right? So what do we know? What are we given, right? This is where we can start underlining something like wavelength, right? 700 nanometers, and the speed of light, right? How we apply to this, let's get to it right now. But I just want you to realize that what we're doing first is finding our knowns. And I'm gonna just write this over here so it's a little convenient as well. Make that a little darker. Is equal to 700 nanometers, right? And this is where I have to make that little side note. This is actually 7.00 times 10 to the -7 meters. This value right here is wrong. So if you got something using this, I will show that answer as well, but just know that that's wrong. This is, let me make the side note for scientific notation. Again, if you feel iffy about this, just feel free to look over it and then come back to this specific time. This is where we continue the work, but this is a quick scientific notation note. So how do we go from here to here? Well, let's look at the little nm over here, right? You notice that one of these has an nm, one of these has an m. Nanometers, right, is actually how do we write this? 10 to the -9 meters, meaning that it takes 10 to the 9 nanometers to fill up a meter. Just like it takes 100 centimeters to make a meter, right? 1,000 millimeters to make a meter. We need 10 to the 9 nanometers to make a meter. So we want to translate to something that it's a little more practical to use. And this is where we introduce scientific notation. Now, there are the typical outline for scientific notation is that the decimal goes right after the first number, so we can always focus on the very first number, and then we kind of translate all with this 10 to the 7. Basically, something like 1 to the 0 times 10 to the 2, for example. This just, if we were to translate this to an actual number, we would have to move that decimal according to whatever we have up here. So in this case, it's 2, and because it's a positive, it tells us it's something bigger, right? Which means we would have to move the decimal 1, 2 times. That gives us 100 with a little decimal right there. So these are the same. This is our way for us to translate. Just focus on the number and then leave everything to the exponent. And then in this case, this -7 tells us that that 7 is really small. We have to move, because it's a negative number, the decimal to the other direction, right? And that's going to be 7 times. 1, 2, 3, 4, 5, 6, 7. So the actual number would be something like, and then the 7 would be there actually. 7, 0, right? And again, meters. It's 700 nanometers, but in this case it would be 0.0000007. Of course, that's really difficult to convey all the time, so we don't do that. We actually just stick to the scientific notation. So hopefully this is a really quick review. More than happy to go over this in more in depth, but an explanation of why we got the nm to meters. Okay, if at this point you skipped the scientific notation part, that's dope. Let's go back into trying to solve this, right? So aside about scientific notation aside, let's go back to this number, using this number specifically and our second number, which is the speed of light. Now it's usually we use a little c, and we can just put this as 2.998 or 3. More people often than not use 3 times 8, 10 to the 8, again scientific notation, meters per second. And you notice that this can be like this, or it can also be shown like this. That s is just telling you that it's 1 over s, right? When it's a negative like that, if you see something like s to the -2, that's the same thing as 1 over s squared, right? So that negative just tells you it's in the denominator, it's something smaller. So you can use either or, they mean the same thing. We'll go back and forth, I'll go back and forth. Use whichever one makes most sense to you. Okay, now we have our known values. This is what we do know. And you'll notice if we look back into our original equation, well, we have the speed of the wave and we have the wavelength. We're really looking for, let's go back to the question, what is the frequency, right? And in hertz per second. This is what we're really looking for. So we have 2 out of the 3 variables we're looking for. We're looking for that last one. We can do some quick switcheroos to get that last equation. So let's do exactly that. Let's adjust the equation. I'm gonna write it down here. C is equal to lambda times f, where lambda is the wavelength, f is the frequency, c is the speed of the wave, and I want to look at for specifically f. So what I'm gonna do is divide both sides by this little lambda. This cancels it out, anything over itself is 1, and we just are left with c over lambda is equal to f, where f is what we're looking for. This is where our attention is, this is what gap we're trying to fill. So let's write this over here to write these other 2 variables. Now those look familiar, right? We can just input c over here, we can put lambda over here. So I'm going to do exactly that. I'm going to write our equation here, and I'm going to put for c the speed of light, which is 2.998 times 10 to the 8, whoa, not negative, meters per second. And in the bottom, 7.00 times 10 to the -7 meters. Now we can do a little bit of math, right? But we're simply going to notice that we have 2 m's, anything over itself cancels out. We have an s in the s to the -1, which we're not going to touch, there's nothing to cancel, but we can use these numbers. Now there's a couple of ways to do this. But then this is why it's super convenient to use scientific notation. You can always focus on these numbers first. So let's focus just on that number. That would be 2.998. Let me pull out my calculator over here. And that is 2.998 divided by 7 gives us this number. Now let me drag this over here so I can write that number down. That is 0.428. 0.428, right? And now we can focus on the second component, right? So that's 10 to the 8 over 10 to the 7. The really nice thing about stuff with the same base, and we're talking about the base, we're talking about this 10 here, right, is that in cases like this, right, when we're dividing two numbers, we can always translate it into 10 to the 8 minus that bottom number, which is -7. So just to clarify, if it's dividing two numbers with exponents of the same base, in this case 10, we can just subtract those exponents. You can imagine the same thing would happen if you had something like 10 to the 8 times 10 to the 2, right? If we're multiplying both of these numbers. Same thing, you can, instead of subtracting, you can add them, right? 8 plus 2 will give us 10 to the 10 as a little quick side note example, right? But in this case, we're dividing them, which means that we get to subtract it. And we have two negatives canceling each other out. A negative and a negative is the same thing as a positive and a positive, which gives us times 10 to 8 plus 7, that's 15, with our little second to the -1 there. Now, technically, the correct scientific notation, we would have to move this one more, right? 4 to 8, and adjust our exponent accordingly. This would be small. This is a smaller number. We're making a smaller number bigger, so we have to make this bigger number smaller over here. 10 to the 14th, and the still -1 is still the same. So this is technically the correct notation for our answer to this question. Let's check that the units match up with what we're looking for. We have s to the -1, and we have s to the -1. This could also have been written as 1 to the s, which also works. It's per second, right? So it's those amount of occurrences per second. That's the definition of frequency. Our units match up, and we feel good about this. Now, remember what I said about giving you, right, a misleading number. If you use this number, which is totally fair, I would have done that if I was given it to it. You would have gotten a number that's just slightly different. I believe 4.28 still times 10 to the 16. You do some quick math, that's a smaller number, which means that there would be a bigger wavelength. So you notice the numbers are the same, but these units would be a little different. Hertz, which is the same thing as per second, right? 1 over s. Now, if you got this number, good, awesome. You know how to work with this equation. You know how to do that. It was just a little mess up on my part. So I apologize again on behalf if that was confusing. I hope it's not super. And I hope that at the very least, the relationship between wavelength, frequency, and light make a little sense. Long story short, we want to always isolate whatever it is that we're looking for. In this case, it's that f, right? So we manipulate our equation so that we can isolate that last variable, and usually we're given our values. Same thing can be applied for the second question of this problem. We have two different frequency or wavelengths, and we need to find the two respective frequencies.